So the bottom line of all this is we've got these periods which are 11-year periods where we have really good propagation conditions because we get a lot of skip, and then we've got periods where the sun becomes dormant and we get less ionization and the bands are pretty dead. So we're in time, right now we've gone through a recent peak. It was about two years ago, and we're now on the downside. So for the next 5 years or so, it's going to be fairly quiet in terms of our ability to communicate. Last month or so, people have been saying that bands are really dead, but they're not. It's not going to be completely dead, but we get periods where it gets better, it gets worse. It's sort of like the weather, and people do solar forecasts just like we do weather forecasts. All right, so we've seen the video showing flares and coronal mass ejections. And okay, so one of the factors that we are interested in is what's called the solar flux, which is essentially the intensity of the energy coming from the sun. So that determines the more solar flux we have, the more energy, the more ionization we have, and the better long-distance communication we can get. So here's one of these. I'm not sure. This isn't really a forecast, but this is a chart of current conditions. Well, it's not current conditions. It's what the conditions at the time we took these snapshots. So if you go to the Delta website, down at the bottom of the page, you'll see one of these forecasts that come from somewhere else on the internet. And there are two forecasts here. There's the one on the top and the one on the bottom. I'll explain the one on the bottom in a moment. The one on the top is what you'd normally see. And there are interesting numbers over here. So SFI is the solar flux index. So that's basically the intensity of the radiation from the sun, which is 90. The SN is the sunspot number, the number of sunspots that people are counting at this moment in time. There's an A factor, which is the stability of the Earth's magnetic field, and there's a K factor, which is the effect of the solar particles, which is particles that have been emitted from the sun on the Earth's magnetic field. Then there are other interesting things that people might not like to know, like the X-ray intensity. The 304A is ultraviolet intensity, and what the others are. So some people like to look at the numbers and see what they are, just like looking at how much rainfall we're going to have or sunlight we're going to have in a weather forecast. On these sections here, we've got the VHF conditions and the UHF conditions, and basically from the raw data we can make predictions on whether or not the bands are going to be good or not. So we'll often see something like this, which is daytime 80 meters to 40 meters are fair, at nighttime they're good because daytime we've got D-layer, at nighttime we've got F-layer reflection. These bands around 30 to 20 meters are good both day and night, and then as we go higher in frequency we get worse conditions because there's not enough ionization to reflect those high frequencies. And that's a fairly typical forecast that you'll see. Over on the right there's a sort of chart to guide you on what some of these numbers mean. So we've got a K number and an A number. So given A5 and K2, so we've got A5 here, K2 here. So we've got quiet conditions. That is the Earth's magnetic field is pretty stable, and we've got fairly good propagation conditions on HF. The one down at the bottom is during a solar storm, and you'll see it's very different to what we have at the top. So the solar flux index here has gone from 90 up to 116. Sunspot number is a little bit higher, but not really. We really notice a big difference in the A factor and the K factor, which will increase to which the name knows. So what's the effect? So this is what we see. We've got a solar storm going on, and the HF is completely dead. There's no communication going on or capable there at all. The note here, major storm. But what's happened is 6 meters is now open, where normally VHF, we get no long distance propagation. We're now getting good propagation at 50 megahertz. And there's another note here that is of interest to people is there's an active aurora. Because some people like to try bouncing signals off the aurora because it is a intense ionized field. So you bounce off the aurora just like you bounce off on the F layer. So those are sort of predictions that you might see. There are lots of things on the internet that you can look at in terms of looking at solar conditions and predictions and forecasts, looking forward on what things are going to happen, because just like the weather, you can look out a little bit. You know roughly what the trend is, and if there's sunspots tend to travel across the sun, so you might see it appearing on the edge of the sun, and you know as those sunspots come round and face the earth, they're going to have greater impact. Okay, question. How come there's no day-night? Oh, down here. Yeah. Well, this is because of the solar flux is so intense. It's basically forming a strong D layer, and that D layer is remaining during nighttime. So at nighttime, it takes time for those electrons to recombine with the atoms and for those layers to collapse. So if you've got a very intense ionization, that can be sustained for a long period of time. Does that make sense?
Yeah. So the D level is supposed to occur, and that's part of
No, the D layer is the absorption layer. You might get VHF off the E layer if there's a strong E layer. Okay. HF usually off the F layer. So the importance of the D layer, so the E layer and the F layer are reflective layers. We get bouncing off the signals of the E and the F layer. The only thing the D layer does is it stops the radio signals getting to the E layer and the F layer. It's an absorption layer. So if at HF, yeah. So if you've got a very intense D layer, so first of all, during daytime, the D layer is stopping low frequency HF signals getting through. But during a solar storm, it becomes so intense that it sustains even at nighttime. So it stops any signals getting through even at nighttime.
So then what happens with VHF frequencies is right through the
Yes. Yeah.
Unless you have the major storm, there's so much energy, then it's going to get that down.
Right.
If you look at the bottom section there, you're doing the storm, now
So the at 50 megahertz, that's penetrating the D layer, and I guess it's probably getting off the E layer. Bouncing off the E layer. Okay, so moving on to more definitions here, I think. What have we got here? We were just talking about the ionization. Oh, MUF. Actually, we're going to talk about MUF in a moment. So there is so you notice that there's a sort of sweet spot in the middle here. As you go up in frequency, you get to a point where it actually stops bouncing, but at that frequency, the radio wave will actually penetrate the F layer and go out into space. And so there's something we call the maximum usable frequency, which is it's the point at which, if you imagine the stone, it's the point at which it plops into the water. It doesn't bounce off the ionosphere, but it actually goes through. So that's a useful figure to know, because if we want to communicate long distances, we need to be below the maximum usable frequency. The MUF is right on the edge of skipping versus going through out into space. So if we go below the MUF, then we get good skip and get long distance propagation. Okay, so this is where I think we're going to talk about some of those things. Again, lots of definitions here. Let's first of all talk about critical frequency. So if we were to fire a radio wave straight up vertically into the ionosphere, and we change the frequency, at lower frequencies it would bounce off the F layer and come back, and we could actually hear the echo. You'd send a pulse up, and you could hear the echo come back. And so what you can do is you can increase the frequency until you stop hearing that echo. At that point, a signal going up vertically is not being reflected by the F layer, but it's going out into space. And that's what we call the critical frequency. And again, it varies according to time of day and solar conditions and everything else. But it's a nice reference point to know what the conditions are in the atmosphere. When we send the signals out at an angle, you get that glancing glow on the ionosphere, and you get reflection. So even above the critical frequency, we'll get bounce at this angle, where if it went up vertically, it would just go straight out. So again, you get this dead spot in the skip zone, where depending on the angle, if the angle is more vertical, then it's going out, and as the angle changes to be more acute, you get a skip. Again, we're not going under water. If you get the right angle, you skip off the water. And that changes with frequency. So if we increase the frequency, even at these angles, we'll get less of that diffraction or curving effect. And so there's a frequency at which we stop getting skip, even at these low angles. And that's what's called the maximum usable frequency. Beyond that, we can't get any bounce off the ionosphere at all. So there is actually a relationship between the critical frequency and the maximum usable frequency, which is, I believe, around 3 times. I'll just check my notes here. It's not in here, but I think it's about 3 times. So if you measure, or if you look at the current conditions and know what the critical frequency is, you can work out what the maximum usable